Welcome back, guys. So far, we explored the rectilinear kinematics. Rectilinear means that the path is a straight line. And we said that if the path is a straight line, I can describe this path using S, and I can find what is V as ds over dt, what is A as dv over dt. Now the question is, all our motions are rectilinear? Of course not. Most our motions are curvilinear. And curvilinear means the path is a curve. So the motion of the particle is traveling along a curved path. This is not a rectilinear path. This is a most general case where the path is a curve. So how can I find the velocity, the acceleration, and all my kinematics variables if I have a curved path? In this part, we're gonna relate our kinematics quantities in terms of rectangular components of the vectors. What does this mean? How can I relate a curved path into rectangular components? Remember, guys, rectangular components means x, y, and z. So these are the rectangular components. How can I relate a curved path to rectangular components? In fact, guys, if I have a curved path like this one, like this case here, right? This basketball case here, I have a curved path. In this case, S is always tangent to this path because, in fact, S is this path itself. However, guys, if I want to find the position of this ball at this instant here from, let's say, this origin here, then R will be this vector. This is R. After a certain time delta t, R prime will be this vector here. So this will be R prime. And this means, guys, that if I have a 2D motion, R could be represented in rectangular components as xi plus yj. Then if I know R in vector form, can I know V in vector form? And why I am saying V in vector form? Because in fact, guys, here in this case, V is changing its direction. If I have a curved path, then at a certain time here, V will be tangent to this graph, like this case where V is horizontal. At another time, T prime here, V is vertical. So this is V prime, let's say, and this is V. Unlike the rectilinear motion, where V is only changing its sense, for example, to the left or to the right, and I don't have to find V in vector form because I know, in fact, the direction of this V, it is in the same direction of S. Right? So if this rectilinear motion is horizontal, then V is horizontal. But this V could change only its sense, positive or negative. Unlike this rectilinear motion, in the case of curved path, V could change also its direction, not only its sense. So V could be at a certain time vertical, and then could be oblique, and then could be horizontal. And this means, guys, since V is changing its direction, not only its sense, I have to find V in vector form. Alright? So V, guys, will be equal to dr, which is xi plus yj over dt. And so And the same goes for the acceleration, where A also in vector form is equal to dv over dt. So this is, guys, how I can find or I can relate my kinematic quantities in terms of rectangular components. An application of curvilinear motion is a roller coaster, right? So if I need to find its position, if I know the speed, or if I know the velocity, how can I find it? Or if I am a kicker and I should know at what angle theta and initial velocity I must kick this ball to make a field goal. Or for a given kick, what should be the angle of the ball to be kicked so that I can get the maximum distance? So guys, in fact, this is what is called the curvilinear motion. I have a curved path. This curved path is represented by S. However, S here is not a straight line, alright? So I should find R in vector form. And then don't forget, guys, that the displacement delta S here, which is S prime minus S, will be in fact the magnitude of delta R, because in fact delta R will be R prime minus R, which is this one, right? However, S will not be equal to the magnitude of R, as you can see in the curved path. Alright, and of course, guys, I should find V in vector form. V average will be delta R in vector form over delta T. V instantaneous will be dr over dt. And this also means that V is along the tangent line of to this curved path at this point here. And same goes to acceleration. But guys, I want you to understand that this acceleration will be along the tangent line to V and not to S, all right? So this V here, this graph of V is called hodograph. In this case, the acceleration will be tangent to this hodograph, but it doesn't have to be tangent to S, all right? So guys, in fact, as I said, you have to represent the vector R using the rectangular components. So this is the representation of R using the rectangular components. It is xi plus yj plus zk. And don't forget, guys, since this is a curved path, x is a function of time, y is a function of time, and z is a function of time. Because if they are not a function of time, then R is constant and there will not be any velocity, all right? So they are in terms of time. And I know, guys, since R in vector form is equal to xi plus yj plus zk, then R in magnitude will be equal to radical x squared plus y squared plus z squared, which is, of course, different than s, all right? So it's, of course, different than s. And then UR will be equal. UR is what? As in statics, guys, UR is the unit vector of R, and of course it is equal to R in vector form over R in magnitude. Now, how can I find V? In fact, I know, guys, that R is equal to xi plus yj plus zk. So if I want to find V is equal to dr vector form over dt. And this means, guys, that I must do the derivative of xy plus yj plus zk, which is also the derivative of xi over dt, and the derivative of yj over dt, and the derivative of zk over dt. And listen up, guys. Since I, j, and k are constant with respect to time. What do I mean by constant with respect to time? A vector is constant with respect to time if the magnitude of this vector is not changing with respect to time, as well as its direction. And remember, guys, remember this fact, right? Because I'm going to use it later on, right? So guys, since I, j, k are fixed, are constant with respect to time in magnitude and in direction, I can remove this ijk from the derivative, and then this v will be in fact the derivative of x with respect to time, which is x dot, I can say it as x dot I plus y dot j plus z dot k, right? assuming that x dot is equal to dx over dt, y dot is equal to dy over dt, and z dot is equal to dz over dt. And guys, this x dot, since it has the direction of I, then I can call this x dot vx. Since y dot has a direction of z, then of y, then I can call this vy. And since this z dot has a direction of k, then I can call this vz. Alright, which means guys, v is equal to vxi plus vyj plus vzk, where vx, vy, vz are respectively equal to x dot, y dot, z dot. Right? Now, how can I find the magnitude of the velocity vector? It's of course the radical of the sum of the squared components of this velocity. And don't forget that the direction of v is tangent to the path of the motion. Now, same goes to acceleration. The acceleration is equal to dv over dt. So if I replace v by vxi plus vy, j plus vzk, and then by x dot I plus y dot j plus z dot k, I, j, k are fixed in terms of time, so I can remove them from the derivative. Then a will be of course equal x double dot I plus y double dot j plus z double dot k, and the magnitude of the acceleration will be of course the radical of the sum of the components squared. And then the direction of a, it is, as I said guys, it's not usually tangent to the path of the particle, but it is tangent to the hodograph, or it is tangent to the curve of the velocity. Now, how can I find the direction of A, guys? Of course, I can find the unit vector of A, or I can find tangent A. If it is in 2D, it would be AY over AX, and this will give me the tangent of the angle between A and the horizontal line. Right? So this is all about the curvilinear motion in rectangular components. A direct application of this curvilinear motion is the motion of the projectile. So let's go over it. Thank you.